Hi time travelers, ever wondered how we track time so precisely? Let us dive into the science behind timekeeping and atomic clocks. Time defines the order and rhythm of events, from our daily lives to the cosmos itself. Sundials and water clocks, used for thousands of years since ancient Egypt and Mesopotamia, were among the earliest timekeeping devices. These early clocks used natural processes like the sun's movement or flowing water, but were disrupted by weather, seasons, and uneven water flow. The invention of the pendulum clock in the 17th century significantly improved accuracy by using a swinging pendulum to regulate time. However, even this advancement was not perfect. Pendulum clocks drift due to factors such as changes in gravity, air resistance, and mechanical wear. By the 20th century, quartz clocks became the standard due to their vibrating crystals, which provided much greater precision. When electrically charged, a quartz crystal oscillates at a steady frequency, ensuring highly consistent ticking. However, like their predecessors, quartz clocks are not immune to drift. Temperature changes, crystal aging, and voltage fluctuations in the circuit introduce small inconsistencies that over time can lead to significant timing errors. Despite their imperfections, these timekeeping devices were accurate enough for daily life and navigation in their respective eras. So why do we need precision clocks? In modern times, even a millisecond error, a mere thousandth of a second, can throw a lunar mission 300 kilometers off course. Why? At light speed, which is 300,000 kilometers per second, tiny timing mistakes translate into massive distance errors. Space missions rely on flawless timing for communication across vast distances. GPS satellites, which rely on precise time signals, experience large position inaccuracies from just a few nanoseconds of drift. The internet depends on global time synchronization for secure data transfers and cybersecurity. High-speed air travel requires ultra-accurate time for safe navigation. This razor-thin margin for error led to the invention of atomic clocks, which measure time using atoms' natural vibrations, making them billions of times more precise than traditional clocks. Without the notion of an atomic clock, GPS, global communications, and space exploration as we know them would not be possible. So let us explore how these tiny quantum beats became humans' most reliable way to track time. Cesium atomic clock. In 1955, physicists Louis Essen and Jack Parry at the National Physical Laboratory (NPL) in the UK built the first atomic clock based on cesium. Cesium, a soft gold-colored, highly reactive alkali metal with 55 protons and 55 electrons, sits in period 6 of the periodic table. Its 54 inner electrons fill 5 shells, while the 55th electron, which is its one valence electron, occupies the outermost shell. This atomic structure makes cesium ideal for timekeeping. Let us see why. In cesium atomic clocks, the stable, high-frequency vibrations of cesium atoms serve a similar role to the swinging pendulum in a grandfather clock. The process begins by heating cesium atoms in an oven to form a beam. The atoms in the beam exist in one of two distinct energy states, or hyperfine states. Let us call them state A and state B. A magnetic field then filters out atoms in state B, leaving only atoms in state A to continue through the system. The state A atoms pass through a resonator, where they are exposed to precisely tuned microwave radiation. This microwave energy energizes some atoms to transition from state A to state B, like dancers leaping up with energy when their favorite song plays. Next, the second magnetic field removes any atoms that remain in state A. A detector counts how many atoms successfully made the transition to state B. The number of atoms that switch states depends on how closely the microwave frequency matches the cesium atom's natural oscillation frequency of 9,192,631,770 Hz. The closer the match, the more atoms make the jump. The system continuously adjusts the microwave frequency until it perfectly aligns with the cesium atom's hyperfine transition frequency. Exactly 1 second has passed once 9,192,631,770 of these oscillations are counted. Atomic clocks are so precise that it would take millions of years to gain or lose a single second, all thanks to the rock-steady quantum rhythm of atoms, the heartbeat of these ultimate timekeepers, shaping our modern world. How are atomic clocks synchronized? Around the globe, atomic clocks are synchronized by regularly comparing their time with one another through a network of satellites and radio signals, overseen by the International Bureau of Weights and Measures, BIPM, based in France. BIPM collects timing data from atomic clocks in national laboratories around the world and calculates the most accurate time, known as the UTC, Coordinated Universal Time. This official world time is then shared through GPS satellites, radio signals, and internet time servers, ensuring that clocks everywhere, from smartphones to space missions, stay perfectly synchronized. So next time you check the time, remember, it's not just numbers on a screen. There is an army of atoms out there dancing to the beat of microwaves, keeping the world running on time. If you found this insightful, subscribe, like, and share. Happy learning. Thank you.